Bismillahirrahmanirrahim. Dear students, I welcome you in this course on Data Communications and Computer Networks, CSC 339. This is our lecture number 1 of asynchronous mode. In this lecture, we will talk about transport layer principles and services. Transport layer provides us a variety of services, and we'll also talk about its fundamental principles. We'll see how we can differentiate in between multiple TCP or UDP connections between host and server using multiplexing and demultiplexing concepts with TCP and UDP. We'll also talk about sockets, TCP and UDP segment structure, what is the fundamental difference between the two, transmission control protocol and user datagram protocol. We'll talk about the reliable data transfer, delivery, the reliable data delivery protocols, and we'll also talk about how TCP's reliable data delivery protocol mechanism works. So the learning outcomes of this lecture is that you should be able to understand the principles and the services that are provided by the transport layer, and most importantly, the working of UDP and TCP, their end-to-end communication principle. You should be able to judge the effectiveness of TCP and general reliability systems. And you should be conversant with primitives of sockets. Before moving forward towards the topics that we have to cover, let me quickly identify that what we have covered so far for session 1. So previously we have talked about the fundamental concepts of in computer networks. We have talked about application layer. In application layer, we talked about application layer architectures. There are 2 types of architecture here. We know that point-to-point and client-server architectures. Then we have identified different types of network applications at the application layer. There are network applications that demand reliability, and then there are network applications that demand speed. So there are applications that are loss tolerant, and there are applications that are data tolerant. I mean, that can the applications can application can accept losses in the transmission of the data. So we also cover different types of network applications, and they're working in detail at the application layer. For example, we talked about email, and while talking about email, we covered different protocols. For example, we talked about simple mail transfer protocol, SMTP, that how mails are transferred from client machine to server and from one server to the other servers. What are the protocol details? And we also talked about POP3 and IMAP for these are used to store emails, searched emails, managed emails on email servers. And then we also talked about web browsing, and we covered hypertext transfer protocol here and its different types. For example, there are persistent hypertext transfer protocols and there are non-persistent hypertext transfer protocol. We also talk about HTTPS. Then web caches means we talked about the importance and need of having proxy servers. Then we talked about DNS, and here we also talked about top level domain servers, and the placement of root DNS and the other details. We also discussed point-to-point protocols, and here we, in detail, we discussed the example of BitTorrent application, how BitTorrent works, what is the trading algorithm of BitTorrent. So we have covered all this in details. And we had a comparison between point-to-point and client-server applications, where we established the fact that point-to-point applications are self-scalable as compared to client-server applications. Okay, let's start with today's lecture. So first we'll talk about transport services and protocols. What services are being provided by the transport layer and the protocols that we'll be covering at this layer. So transport layer provides us logical communication, right? Between application processes means there may be an application process running on this machine here, and the other application process is running maybe on the other machine on the other side of the planet, right? So the job of the transport layer protocol is to provide logical end-to-end communication. By saying logical end-to-end communication, we mean that transport layer is really not concerned about the many different routers or data link layer protocols or links in between source and the destination machine. So irrespective of different links in between the host and the destination machine, the transport layer provides us process-to-process communication. And we'll try to elaborate this with the help of a scenario in a minute. So at the end, when an application has to transfer something to the other end, so whatever is coming from the application layer is encapsulated into a segment at the transport layer. At the receiver side, these segments are assembled, combined, and the data is forwarded to the application at the application layer on the destination. So the protocols that we'll be covering here, these are two basically: transmission control protocol and user data graph protocol. TCP is connection oriented, whereas UDP is connection-less. So let's try to elaborate these points with the help of a scenario. Okay, so let's assume that we want to make communication possible between two machines. So we have machine A and machine B here. There is a core network between the two machines, where we have multiple routers, for example. So this machine A is connected to, say, router R1. I'll label it in a minute. And say this router is connected to R2, and R2 is connected to, say, R3. And there is another direct connection between R1 and R2. And this router is connected with the other machine. So here we are saying that this is machine A connected with machine B with the help of this core network, where we have router R1, which is connected to router R2, and there is another connectivity from R2 to R3, and R1 is also directly connected with R3. And in this scenario, we can have we can have a complex scenario where there are many routers are involved in order to reach from A to B. So there are different types of connectivity here that we need to identify. So one connectivity is that this machine A is connected to R1. So this is one type of connectivity where A is connected to R1. So see, A is one node and R1 is another node. So we can call it, this is, we can call it node-to-node connectivity. Right? So where one node is connected to another node, right? It means A is one node, R1 is another node, so A is connected with R1. Similarly, this is also node-to-node connectivity, right? Where R1 is connected, with R3, and obviously the link between R1 and R2 is also node-to-node connectivity, and similarly the link connecting R2 and R3 is also node-to-node connectivity. And also on the other side, this router R3 is connected with the destination machine, say B, and this connectivity between R3, router 3, and B is also node-to-node connectivity. So, so this is the general symbol that we use, or notation that we use for router. Okay, so this is one type of connectivity here. By the way, this type of connectivity is the responsibility of data link layer. So data link layer is responsible for providing node-to-node connectivity, right? So in order to reach from machine A to router R1, we need to have the physical address or the MAC address of this router R1, or this port of router R1. So if I want to connect these two machines together, so yes, I need to have the MAC address, okay? Right, but there's another type of connectivity here. And this connectivity is between machine A and machine B, where machine A is connected with machine B, right? And this type of connectivity is called end-to-end. End-to-end connectivity. So you can clearly see A is one end in this scenario, A is one end and B is the other end that we want to connect to, right? So the connectivity between the two ends is known as end-to-end connectivity. And this is the responsibility of network layer. So in our reference model, OSI or TCP IP model, this is the responsibility of the network layer. So if I want to reach from machine A to machine B, so you can see there are many different routers involved in between. So I need to make a routing decision here. So for example, at R1, from reaching machine A to R1, I need to make a decision. Either the data will be forwarded to machine B through R2, or data will be forwarded to machine B through R3. So here we have to make a routing decision, and you can see in a real-time scenario, it's a complex problem where we have many different routers involved in between. So here we have to make a routing decision. So MAC address is not enough for me here. So if I want to reach to machine B, obviously I need to have another address. And this time I need IP address for this purpose. Why? Because IP address is hierarchical and means we can make routing decision based on the information in the IP address, right? So this means if I want to reach from machine A to B, there are many different types of links involved in between. So this link can be, for example, wireless. At the moment, it's wired link, and this link can be, based on Ethernet if it is not wireless, or maybe it's based on Wi-Fi, right? So there are a variety of links, there are a variety of routers, there are many links in between, right? So I can reach to other machine using what? Using IP address. But reaching to other machine is not enough. Why? Because because at any machine in the network, there are different processes going on. For example, at machine A, I'm having HTTP protocol. There's a process representing HTTP protocol. Maybe I'm having SMTP protocol, or I'm transferring a file. For that, I have FTP protocol. And similarly, on machine B, there are different processes going on. Right? For example, FTP, and then we have maybe SMTP. Remember, all these protocols and applications we have covered at the application layer, or HTTP. So reaching at machine B is not enough. So we also need to identify which process of machine A will be communicating to which process of machine B, right? So for example, if I want to complete this end-to-end communication cycle, so I need to identify, for example, I'm just assuming that HTTP process of machine A will be communicating to the HTTP process of machine B. So there is another type of connectivity here, right? So what do you think, what type of connectivity this is? This is, yes, you're right. This is process to process communication or connectivity. And what do you think, which layer is responsible for this process to process communication? Yes. Transport layer is responsible to provide us this process to process communication. So see, if we were trying to reach from machine A to this port of router R1, so we need to have the MAC addresses, right? And if I want to reach from machine A to machine B, and there we have to make routing decisions in between. For that, I need to have the IP address. So what about providing this process to process communication? What do you think? Do we need to have any process ID or address? Yes, we do, right? So if I want to identify um, the process of machine A, which process of machine A will be communicating to which process of machine B, I need to identify these processes. And I can do this with the help of process IDs, which are called port numbers. Right? For example, for HTTP, we have port 80. For SMTP, we have port 25. For FTP, we have port 21, right? So these are port numbers that we have to use in order to tell machine B that it has to forward this data that is coming from machine A to port 80, which is representing HTTP process. Okay, so when we say the transport layer provides us process-to-process logical communication, this means number one, it enables process-to-process communication because without it, we won't be able to complete this communication process. Number one. Number two, here the transport layer is not bothered about the links in between A and B in this scenario, and the types of link and the technology that is being used at the data link layer. So irrespective of the technologies and the links and the number of links, transport layers provides us process-to-process communication. Now, if we have to um, forward data using, for example, HTTP from machine A to machine B, so whatever we are sending, um, whatever is being sent by the application layer will be encapsulated inside a segment at the transport layer. So let's try to understand this concept. So remember the layered model that we covered earlier. So there we have different layers. For example, we have physical layer. Then we have data link layer. Then we have network layer. And on top we have transport. And at the top, by combining the upper three layer, we can have the application layer, right? So this is a hybrid model that we have discussed earlier. So whenever any application transfer data from machine A to machine B, the data is first forwarded from application layer to transport layer. So whatever we want to transmit will be encapsulated inside a protocol data unit, which is called a segment. Basically, it has two, broadly speaking, two parts. One is header, and the other is the data or the payload field. So this is called segment. For TCP, we call it generally the notation is to call it TCP segment. For UDP, we call it UDP Datagram, but Datagram is also used for the protocol data unit at the network layer. So for simplicity, we'll call it either this is a TCP segment or a UDP segment, because there are two types of protocol at the transport layer that will be covering, either TCP or UDP. Okay, so as the data is transferred from transport layer to network layer, this TCP or UDP segment is encapsulated inside a datagram. Okay, so broadly speaking, datagram has also two parts, header and the payload field. So this means this TCP or UDP segment will be encapsulated inside the payload field of the datagram. By the way, in the TCP or the UDP datagram header, there are many different fields, but two fields are important here to identify. Can you guess? Yes, right. So there are two fields identifying the port number of the sending process and the port number of the receiving process. Similarly, in the datagrams header field, there are many different fields, but two fields are very important. Can you identify with this, with the relevance of this scenario? Yes. One field is the IP address of the sending machine, and the other field is the IP address of the destination machine. Okay, as the data is moved from network layer to data link layer, so this datagram, which is encapsulating TCP or UDP segment itself is encapsulated inside a frame, right? So this we call it at the data link layer, it's a frame. Okay. So frame also has, broadly speaking, two parts: header and the payload field. The data of the payload field will be encapsulating the datagram coming from the network layer. And also, again, if we look at the header field, it has many different fields, but two fields are important considering the scenario. Yes, you're right. One field is the MAC address of the sender in this scenario, and the other field is MAC address of this port of router R1. By the way, if I make a decision to send data from R1 to R2 to follow this path, for example, what will be the source MAC address and what will be the destination MAC address when the data is forwarded from R1 to R3? So we'll be having your answers in our live session. So are we clear about the datagram or the encapsulation process? This whole process is known as encapsulation process. And similarly, on the destination side, we have this decapsulation process where the receiver will first receive a frame, then the receiver will decapsulate datagram, and then it will decapsulate, extract segment out of it. And by just looking at the header of the segment, the data will be forwarded to the respective process at the destination machine. Okay, so I hope we are clear about the logical communication property of the service of TCP, what we really mean by saying logical communication. And now we also know that whatever is being forwarded by the application layer will be encapsulated inside a protocol data unit, which is called a segment. And we can have more than one segments to accommodate the data that is coming from the application at the application layer. And at the receiver side, will be assembling, combining the data from these segments and will forward it to the application layer. Okay, so here it's very important to identify the difference between the network layer and the transport layer. So network layer, as we have just seen in this scenario, provides us logical communication between the hosts or the ends. So the responsibility of the network layer is to provide logical communication between the two ends, regardless of the links in between, regardless of the core network here, right? And the protocol data PDU means protocol data unit at the network layer is known as datagram, IP datagram, or IP packet. IP fundamentally is connectionless. So this means a datagram can be reordered, is duplicated, or maybe is lost. So IP has this best effort delivery. Right? There is no acknowledgement, or there is no reliability in IP fundamentally. And whereas if we talk about the transport layer, it gives us logical communication between the processes, right? So by saying logical communication, we have already covered that irrespective of the links in between, it provides us communication between the processes of sender end at the destination machine, right? And the protocol data unit at the transport layer is known as segment, right? So basically, the important thing is the transport layer extends the end-to-end communication provided by network layer to process communication. Obviously, we have covered this earlier as well, that upper layers use services of the lower layer. So upper layer, in this case, transport layer is using the end-to-end, in fact, is extending the end-to-end or host-to-host communication to process-to-process communication. And it's also challenging as well, because at the transport layer, we are also having this reliable protocol TCP, whereas network layer, the layer below is not providing any reliability. Can transfer packets out of order, IP packets can be duplicated. So we'll see, this is a very interesting thing to be discussed in coming slides. So there are two types of protocols that we'll be covering at the transport layer. The one is reliable, provides us in-order delivery, and we call it TCP, Transmission Control Protocol. These are very important aspects that we'll be covering at the transport layer because it provides us reliability. It is also complex. So we'll be talking about its connection establishment. We'll see how we maintain or control the flow of the data. And we'll also be talking about the congestion control mechanisms of TCP. Whereas UDP, user datagram protocol, is unreliable. Means we can have unordered delivery of segments. So there's an obvious question here. What do you think? What does UDP provides in addition to IP then? Well, one point we have already identified, that it extends the host-to-host communication provided by IP to process communication. So what does it is really adding on top of network layer to IP. Right. So again, this is another question that I want to have answers in our online sessions. We'll see what you come up with. So there are services that are not provided by the IP. For example, delay guarantees, bandwidth guarantees that can be provided by the protocols at the transport there. So the next topic, which is very important to understand, is multiplexing and demultiplexing. So when a receiver receives data, for example, let's consider this scenario that we have already discussed. When A is sending data to B, when B receives data, it does not directly transfer data from transport layer to the application layer. Right. So there's an interface, or you can call it doors through which data is forwarded to the application layer. Right. These interfaces or doors between the processes and host are known as sockets. So at any point in time, we are doing multiple things using our machine or PC. I'm browsing internet also. At the same time, I'm downloading or sending files. I'm maybe sending email or checking the status of other machine by using, say, I'm telnetting, running a telnet command here. So how to differentiate the data of these different type of protocols? So for that, we need to have multiplexing and demultiplexing. So for that, we identify a socket, which is sort of like a door in between application and the transport layer. So a socket is basically, so if I want to identify a socket, it has basically, in its fundamental form, it has two entries. For example, we need to identify the port number and the IP address of the other machine. So having this combination, I can identify any specific type of traffic that is being generated on the sender side, or data that is being received at the receiver side. By the way, this simplest form where I have two entries, port number and IP address, defines the socket of UDP, user datagram protocol. So I have the destination IP, which will take me to the destination machine, and then I have this port number which will help me to identify the process that I have to forward this data to, right? So IP will help me reaching this machine. Say this is the destination, and there are many processes going on here. So I'll use this port number to decide which process I'll be forwarding data to, right? So this process at the destination is known as demultiplexing, right? And on the other side, at the sender machine, for example, there are many different processes going on here at the application layer. So data from a process through sockets will be forwarded to the transport layer, right? So this is known as multiplexing and demultiplexing. And what do you think, why it's important? Yes, it's important because we want to differentiate between the several communication channels that are taking place between machine A and machine B, or maybe any other machine. So we need to differentiate, and we can only differentiate it with the help of this logical opening, or this door between the transport layer and the application layer. So if we talk about the TCP socket, so instead of 2 entries, we have 4 entries. So we have to identify, first of all, the source IP address, right? So the source IP address, and then a source port number, and then also we need to identify the destination IP address and destination process address. What do you think? Why do we need to identify? Why do we need to have 4 entries here? Yes, you're right. Because TCP is connection oriented. By saying connection oriented means we'll be having acknowledgements. So when I'm sending data to the destination machine will send me an acknowledgement to confirm that the data has been received by the destination machine, right? So in order to ensure the reliability. So for that matter, I also need to identify the source IP address and source process address, in addition to have destination IP address and destination port number. Okay, so if we talk about UDP sockets, there are 2 tuples, 2 entries, destination IP address and destination port numbers, right? So the host, the receiver, when it receives data, checks the destination port number and makes a decision which process will be receiving the data, right? It directs the data to the specific process having the specific port number, right? IP datagram can have different IP addresses and different source port numbers directed to the same socket, depending upon the number of connections that a machine is having with the other machine or other machines. Whereas if we talk about TCP demultiplexing process, means where we have to ensure connection oriented communication, means the acknowledgements are there. There are 4 entries. First of all, we need to have the source IP address, then we need to identify the source port number, the process address of the source machine, and then the destination IP address, which will take me to the specific destination. And then also I need to have the destination process ID, which is destination port number, right? Why? Because I can have a multiple connection with the other host machine. I can have simultaneous TCP sockets. For example, remember we talked about non-persistent HTTP, in which with every subsequent request we have to again initiate a new connection, right? So non-persistent will have different sockets for each request. So for every HTTP non-persistent HTTP connection, I need to establish a TCP connection first. And if you remember, for every non-persistent HTTP connection, I have to establish connection for every subsequent request. So there will be a new connection. I have to identify the sockets for each subsequent connection in this case. Okay, so let's talk about TCP and UDP in detail. So first of all, we'll talk about user datagram protocol. The details of user datagram protocols for a developer can be are given in request for comment 768. So we have already covered it that UDP is not adding much into the services that are provided by the IP, because IP is connectionless, Internet Protocol at the network layer is connectionless, and UDP is also connectionless. So it only extends host-to-host communication provided by the Internet Protocol at the network layer to process communication. So we have already covered that UDP segments may be lost, can be delivered out of order. It also provides us best effort delivery. Then there's an obvious question that why do we use UDP then? So there are certain reasons, and by the way, there are many applications that make use of UDP, like DNS, RIP, Routing Information Protocol, SNMP, and there are many real-time applications that prefer using UDP. Why? Because of the following reasons. Number one, UDP is critical for the performance of some of the applications because we don't need to establish a connection first. So if we have to establish a connection, so for example, if I take a TCP for an example, so I have to establish a connection using three-way handshaking, right? So I'll send a message segment to the server machine. It will be responded by the server. Then I'll again send another segment. Means I'll be sending three segments before establishing a connection with the server. So there is no connection establishment cost in this case. So this really makes it fast as compared to TCP. Then since there is no connection establishment, I don't need to maintain any state of a connection. So what do you mean by state? In the case of TCP, I have to maintain sender and receiver buffers. I have to maintain sequence numbers and acknowledgement numbers of these segments that are that are transmitted or acknowledged. So there's no such state to be maintained in the case of UDP. And UDP has, in a minute we'll see, UDP has a small segment header size, only 8 bytes. So it takes less time to be processed, and that's why it's fast. And we can always have a finer application control over the data transmission. Means UDP is, yes, connectionless. There can be losses, out of order delivery of segments, but this can be controlled at the application layer by the programmer. Obviously, this will be adding complexity into the application. It will be a challenging task for the programmer of an application. So if we look at the TCP segment structure, remember, we just talked about that, about the UDP segment, or the segment at the transport layer. We said, broadly speaking, it has two parts, a header and a data field. So here we are trying to expand the header. We would like to see what are the different fields in the header. Remember, I told you there are different fields, but two fields are very important. One is the process address of the sending machine, and the other is the process address of the receiving machine. So we have destination port number, and then we have source port number. And then we have the length, the total length of the UDP datagram, including header as well as whatever data that is coming from the application layer. And here we have checksum. Checksum is used for error detection. We'll be covering checksum and other error detection mechanisms at the data link layer. Here I have two questions for you to be discussed in our online session. What do you think? Why do we need to have these port numbers, these process IDs? Because operating system is already generating IDs for the processes that are running in a machine. So what do you think? Why do we need to have separate process IDs? So let me write it here. Why separate process addresses for network application processes? Network application process. So I would like you to discuss this in our online session. Secondly, this error detection mechanism is also implemented at the lower layers. What do you think? Why do we have to implement it at the transport layer being part of UDP segment structure? So we also do this, error checking at data link layer. What's your take on this? That we are also doing it at the transport layer. So this is the second question that I would like to discuss with you in our online session. So I've already identified there are many real-time applications that make use of UDP, user datagram protocol. Why? Because these applications are loss tolerant. Remember, UDP is connectionless, and you can see there is no such information in the header of this UDP segment that talks about the acknowledgement or reliability. It's a very simple 8-bit, very simple, uh, 8 bytes header. Very simple, right? That's why it's fast, easy to process. And these applications are rate sensitive because this time is important here. The rate at which we are sending the data is important. So that's why many applications, real-time applications, multimedia streaming applications, prefer using UDP, user datagram protocol. But on the other side, about 75% of the real-time applications are using TCP also because of the reliability it is providing. So it entirely depends upon the designer or the programmer of the application to make a decision either UDP is required or TCP. Other protocols that makes use of UDP is DNS, SNMP, RAP. By the way, here for the source port number, we have 16 fields. This means we can have in total 65,535 total port numbers. And out of these 65,535, the port numbers from 1 to 1023 are standardized, right? For example, we have port 80 for HTTP, we have port 25 for SMTP, and we have port 21 for FTP, right? And the other details we want to look at can be seen in RFC 3232, right? Regarding what? Regarding the assignment of port numbers. Okay.